Okay, so x squared plus 4x minus 1 equals 0. That's a quadratic equation. We have a couple of choices. We could try to factor it. But when you think about that, like, are there any numbers that you can multiply together to make a -1 and add to make 4? There aren't. So we're going to have to use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And what are my a, b, and c in this case?
1 and 4,
That's right. Okay, so this is going to be the opposite of b. If b is 4, the opposite of b is -4. Plus or minus the square root of b squared, which is 16, minus 4 times a times c, all over 2 times 1. So I just replaced everything. And then I have -4 plus or minus the square root of, I have -4 times -1, which is +4. So 16 plus 4 is 20, all over 2. You could just circle that. I'm not overly concerned with simplifying, but I do want to simplify it in the event that the answer in the back of the packet or something looks different than what you came up with. You need to know that they're the same. You need to be able to recognize them as the same, even if you didn't automatically do that. Okay. So how do I simplify radical 20?
Take 4 and 5 out of it. 4 is the square.
Yes, so I can rewrite 20 as 4 times 5, right? And then I can take the square root of the 4. So this becomes -4 plus or minus 2 root 5 over 2. And then you can divide the 2 into both terms of the numerator. So we end up with -2 plus or minus root 5. That make sense? Okay, we all remember the quadratic formula? Okay, so we're just going to do the same thing on this one, quadratic formula. In this case, a is 1, b is 4, and c is 6. So we have -4 plus or minus the square root of 16 minus 4 times 6 all over 2. So this is -4 plus or minus the square root of -8 all over 2. And then how do you deal with a negative under a square root? You make it an I. So you pull that negative out of the square root and you call it an I. So this becomes -4 plus or minus I root 8 over 2. And then you could simplify I root 8, or the root 8. 4 times 2. Think of 8 as 4 times 2, and then take the square root of the 4. So this becomes -4 plus or minus 2I root 2 all over 2. And then you can divide the 2 into both terms of the numerator. So you get -2 plus or minus I root 2. Now, if you had just circled this one, totally fine. Okay. I just need you to be able to recognize that if you got this and someone sitting next to you got this, you can look at it and go, oh yeah, same thing. Right. Okay, everybody remembers a little bit about I, square root of -1? All right. Okay, good. No. Okay, so now we have a function f of x. Some unknown constant a times x to the 4th minus 3x squared minus 4, right? I'd like to know what a is, and I'm given this piece of information that f of 3 equals -150. So f of 3 means plug a 3 in everywhere you see an x, right? So this is going to be a times 3 to the 4th minus 3 times 3 squared minus 4. And what should I get when I plug that 3 in everywhere? Right. So now the only unknown in that sentence is a, and I can solve for it. So this is 81. I think that comes out to 50. 50a is -150. So A is -3. Good. All right, so we're going to need all these skills today in today's lesson. Quadratic formula, we're going to deal with imaginary numbers, and we're going to be solving for A's sometimes. But we are continuing to discuss polynomial functions. Okay. So when you're finding zeros of a polynomial function, what kind of numbers can you get? You can get nice pretty ones like -3, or a half. That's even a nice number, a half. But √2 and -√2, those are called irrational. Don't like those. And then I have -4 + 5i, -4 - 5i. Those are called complex. Right? So we can get rational. That's like integers or fractions. Those are rational. You can get irrational. That's when you have square roots. And then you can also get complex numbers, and that's when you have i's. 3 different kinds of zeros. So here I have a polynomial written in completely factored form, where all my factors are linear. So I want to find all the zeros of this polynomial and classify them as real, non-real, imaginary, complex, rational, irrational. All right, so my zeros are, somebody give me 1 0 of this function, -3. What else? Yes, it shows up twice, yeah. Multiplicity too, yeah. 1/2. What else? If 2x - 1, if you set that term, that factor equal to 0, and solve for x, you'd get 1/2. Okay. These next two, x + √2 and x - √2, solve them, you're going to get plus or minus √2 as your zeros. And then I have 4 + 5i and 4 - 5i. So I can write that, I'll write those together, 4 ± or minus 5i. Those are another 2 zeros. Okay, so I'm going to classify each one of these. -3 is rational. 1/2. It's rational. The definition of rational, remember, is that you can write it as a ratio, right? The root of rational is the word ratio, meaning like a fraction. So you can do 1/2 as a ratio. Plus or minus √2, irrational. And 4 ± 5i, complex. What's the degree of that polynomial? If you were to multiply all those things together, what would be the highest power on x? After you multiply it all together, you do all those multiplications. How'd you get 7? Counted all the parentheses. 1, 2, 3, 4, 5, 6, 7. Because each one has an x, and you're going to multiply them all together. So I don't have to actually do all the multiplication. I can just imagine eventually at some point in that multiplication, every single x is going to get multiplied together, which means I'm going to have a 7th degree polynomial. And how many linear factors are there? How many sets of parentheses are there? 7. Each set of parentheses is a linear factor. How many zeros are there? If we count repeated zeros as separate, like we'll count this as 2 zeros. 7. Yeah. You guys caught on. Yeah. All right. Here's a cubic polynomial. F of x is x cubed plus x squared minus 5x minus 2. We're going to find the exact values of all the zeros of this polynomial. By exact, that means do not put anything in your calculator. If there's a radical, just leave it a radical, right? And then we're going to write this thing in completely factored form. So before I even start, how many zeros is this thing going to have? 3. It's degree 3. It's going to have 3 zeros. How many linear factors is it going to have? 3. Okay. So we can use a graphing calculator to find one nice integer valued 0. So I gave you a little screenshot here. And you can see that the graph of f of x crosses the x-axis right here at 2. Right, so I have 1 0 x equals 2. And I found that graphically. Yeah, there's actually 3, right? But these two, it's hard, they don't cross at an integer point. It could be like negative 2.7 or something. So, but this one goes right through, right, the integer x equals 2. Okay. So now that we have a 0, we also have a factor, right? Zeros and factors come together. So what is the factor that goes with x equals 2? X minus 2 is a factor. X minus 2 is a factor. Okay. Then we're going to use polynomial division. We learned that last class, to find another factor of the polynomial. If we have one factor, we can divide to find another factor. All right, so it was x cubed plus x squared minus 5x minus 2 divided by x minus 2. So a little review from last class. All right, what do you multiply x by to make x cubed? X squared. And then we multiply, we have to distribute that x squared to x and negative 2. So x squared times x is x cubed. X squared times negative 2 is negative 2x squared. And we subtract. Okay, so the x cubes go away. And then I have x squared minus negative 2x squared, 3x squared. And we bring down the minus 5x. And then you start again. What do you multiply x by to make 3x squared? 3x. So I put a plus 3x up here. 3x times x is 3x squared. 3x times negative 2 is negative 6x. And I subtract. The 3x squareds go away. Negative 5x minus negative 6x is x. This is negative 5 minus negative, so it's really plus. Negative 5x plus 6x is x. Bring down the minus 2. Works out so perfectly, yeah. And then x times what gives you x? 1. Distribute, you get x minus 2, subtract, remainder 0. Yo, yeah.
What about the synthetic division?
You do not have to know synthetic division.
It's easier.
So, well, you can learn it if. Okay, let me talk about synthetic division for a second. All right, hold on. All right, so synthetic division is what my math lab will tell you to do, like whenever it does division. It will always give you the same answer. It's just an alternative algorithm to coming up with the answer to a polynomial division problem. If you learn that, if you watch the videos in my math lab and you like that, go ahead and do it. That's fine. I personally like to teach this one because it looks like long division with numbers. So I can build on something you already know. And we won't do this often enough, in my opinion, that the synthetic division is going to save you that much time. You know, you'll do this this does take longer than synthetic division, but I think it's easier to understand. But that's totally just my opinion. So you can do whichever one you like. Okay, so I now know that x cubed plus x squared minus 5x minus 2 can be written as x minus 2 times x squared plus 3x plus 1. Right, that's what the polynomial long division did for us. It allowed us to find another factor. Okay. So our goal from part A, right, remember, go back up, go from part A, is to find all of the zeros, right? I want to find all of the zeros and all of the linear factors. So I have found one linear factor, and this other factor that I just found, is that linear? No, what is it? Yeah, it's a polynomial, it's quadratic. Yeah, it's a quadratic polynomial. So we're not quite done, right? So no, We don't have to do division, right? If I'm trying to find zeros, in general, how do you find zeros of a function? You set it equal to 0 and solve it, which often involves factoring, right? So I want to set that thing equal to 0 and solve it. I now have it written as a multiplication problem, right? Which means either x minus 2 is 0, or x squared plus 3x plus 1 is 0. This one says x equals 2, right? We already knew that. We figured that 0 out from our calculator. And then how do you solve that? Quadratic formula. So x is going to be -3 plus or minus the square root of 9 minus 4 all over 2, which is -3 plus or minus root 5 over 2. So there's my other two zeros. So now I have found 3 zeros. That was my goal. I wanted to find the 3 zeros of my cubic polynomial. So I can list my 3 zeros. I've got 2, -3 plus root 5 over 2, and -3 minus root 5 over 2. And if you know zeros, you automatically know factors, right? If 2 is a 0, then x minus 2 is a factor. If -3 plus root 5 over 2 is a 0, then x minus that monster is a factor. And -3 minus root 5 over 2, if that's a 0, x minus that whole thing is a factor. Exactly. I'm working backwards. I got the zeros first. Whichever one's easier to do that one first, because as soon as you have a 0, you have a factor, or as soon as you have a factor, you have a 0. So whichever one's easier, do that. Yeah. What's the degree of this polynomial? 3. How many linear factors does it have? 3. 3 zeros. Yep. Okay, so some conclusions about polynomial functions based on our example. If a polynomial function has degree n, if you count multiple roots separately, like if -3 is a root with multiplicity 2, if you count it as twice, -3 and -3, right, then the equation will always have exactly n complex zeros. If you count the real and the non-real together, you'll have n zeros. A complex number could be real, right? Like 5 plus 0i. That's just the number 5, but it's a complex number. That's a little, yeah. So it will always have exactly n zeros. Some of them will be real, some of them will be complex. You would just say 5. I was just saying that it is a complex number, even though it's a real number. Yeah, it's real, yeah, yeah. Yeah, hold on. I'll do a separate page. Yeah, so like if you think of a Venn diagram of numbers, right, then we would call these complex numbers, which look like a plus bi. And within there are real numbers and imaginary numbers, right? So like 5 is in there. 5 is a real number, but it's also a complex number because it could be written as 5 plus 0i. 3i is imaginary, strictly imaginary. It's got no real part. Okay, a real world application for an imaginary number. So I actually was just talking to some of my students who are studying engineering, and they said that there's this really cool like transformation that you can do that allows you to do all your arithmetic with imaginary numbers and avoid doing any calculus. So like if you know imaginary numbers, you can avoid doing a calculus problem. They also pop up within the calculations of a lot of real world things, but then all the i's kind of disappear as you go through the steps, and then at the end you get a real number. So like you might not see imaginary numbers like in nature and the universe and stuff.
That's what I wanted to see.
but they're like intermediate kinds of things. Like they pop up in calculations in physics a lot. In oh yes, they show up, but they're more intermediate. Yeah. Yeah. Yep. All right, sorry, let's go back to our conclusions. Hey, up here. Okay, conclusion B. An nth degree polynomial can be written as the product of a non-zero constant, that's the a that we were talking about in the preview exercises, plus times n linear factors. And each linear factor would look like x minus c, where c is one of your zeros. If a plus bi is a zero, with real coefficients, blah, 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 then a minus bi is also a zero, right? Think about our preview exercises. When we solved that quadratic equal to 0, -2 plus I root 2 and -2 minus I root 2 both happened. And that it's just a consequence of the plus or minus in the quadratic formula. Okay, so if you have one complex zero, you have another one. And it's called the conjugate. A plus bi and a minus bi are called complex conjugates. And they always occur in pairs. So do irrationals, right? Like in also our preview exercises. We had 1 plus or minus root 2, 1 plus root 2, and 1 minus root 2. They always show up in pairs like that because of the quadratic formula. Okay, finally, find a third degree polynomial. So it's going to be some x cubed polynomial. Real coefficients. It has -3. That's one of my zeros. X equals -3. X equals I. It's a second zero. But if it's a cubic polynomial, if it's third degree, it's going to have 3 zeros. I only gave you 2. What's the third one? -I, the conjugate. Because this is 0 plus I, right? Its conjugate would be -I, 0 minus I. So you actually have 3 zeros here. So if I give you 3 zeros, then I've almost given you 3 factors. All right, so f of x, we have some unknown leading coefficient. I'll call that a. And then my linear factors are going to be x plus 3, x minus I, and x plus I. And then how do I find out what the a is? Yeah. This last piece of information I gave you. F of 1 equals 8, so I'm going to put in 1 for x. F of 1 is going to be a times 4 times 1 minus I times 1 plus I, and that's supposed to give me 8.
So you just did x.
Yes, I did 1 plus 3, I got 4. Yeah. I put in a 1 for this x, and I added in my head. Yeah. Okay, so now I just have to multiply these 3 things together. We learned how to multiply complex numbers. I can't remember what it equals. I think I'm going to have to FOIL it. I don't think I can do it in my head. Yeah, I'll FOIL it. So I have an a, I have a 4, and then this is going to be 1 plus I minus I, so those will cancel, minus I squared. But what was I squared again? -1, yeah. So I've got a times 4. So this says 1 minus -1, which is 2. So this says 8a equals 8. So what's a? 1. So I'm not quite done yet. That's not my answer, right? Because the question was to find a polynomial. But now I know that my polynomial is this thing that I wrote up here, f of x, but instead of a, I put a 1. So I'm running out of room. I'm gonna put this on a new page. Okay, so now I can replace the a with a 1. So f of x is just x plus 3, x minus I, x plus I. So that is my function in completely factored form. But I asked you for 2 different forms. Let's go back and read the question. It says, give your answer in both factored form, right? We just did that. And standard polynomial form, which means multiply it all out. So it looks like something times x cubed plus something times x squared plus something x plus something. So now I just have to multiply this all out. So I've got f of x is x plus 3 times, and when I multiply this all out, you just FOIL it or use the box, however you learned to multiply these 2 things. So you have x squared, then you have plus ix and minus ix, so those will go away. And then you have minus I squared. So f of x equals x plus 3 times I squared is really -1. So this is minus -1, so x squared plus 1. And then FOIL these 2. X cubed plus x plus 3x squared plus 3. Yeah. Okay. So the directions for tonight's homework says, use the rational zero theorem, Descartes' rule of signs, and possibly the graph of the polynomial function shown by a graphing utility as an aid in obtaining the first zero. Just ignore all the references to the rational zero theorem and Descartes' rule of signs. I did not teach those to you, and you don't need them for any of your homework. You're just going to do what we did in class. You should use a graphing utility. You can use a graphing calculator or GeoGebra when you're doing your homework to find a nice rational zero. So you're going to just find a nice x-intercept of whatever the function is and use that as your starting point, right? Just like we did with the 2. If you go back up here, we found a nice rational zero using a graph. That's what you're going to do in your homework. So just ignore the directions that say use Descartes' rule of signs or the rational zero theorem. All right, so now you're going to do some stuff on your own.